So you were telling me about the course. By the way, somebody wrote something? No. Okay, let me keep this. Ah, so Dana just joined us. Hello, Dana. She will hear us.
Hi, Miss.
Hello. Dana, do you mind turning on the camera? It's up to you, actually. All right? So back to you, Leah. So you're doing forces in the course, you said, right? And
yes.
You said it's going good. Can you tell me a little bit about the attendance? How many students are you in the course? Same as the lab, 8 students?
Yes, same, yes.
Okay. And how's the attendance? Like nobody attends or half the class?
Rima was able to join actually before, but then she was really tired, and she told me that she'll not be able to join this session. And I don't know.
For the others, you don't actually look, probably.
I think Michelle was there, and Joseph was not able. I think he was going to the airport or something like this.
Yeah, I know Nazih usually joined us.
Nazih, yes, Nazih was also in the session.
Yeah. Anyway, I'm gonna talk to them and see why they're not attending. I already did, and I'm gonna do that every single week, okay? Because I want you to understand many issues happening in the lab, and the only way to do so is through us meeting at some point. All right, so I want us first to answer all your questions related to lab 1, 2, 3, if you have any, before we move to lab 4. So Dana, Carl, and Leah, do you have any questions related to lab 1, 2, 3? I'm gonna, as I said in your absence, Dana, I'm gonna put our deadlines from now on to be on Monday evening, so I can give you the chance to probably ask some questions during our sessions and maybe update your lab report before submitting. For today, I'm gonna update the deadline, and if you still need to update or do something, you can submit again. I always take your last attempt to be your actual lab report. Okay, so same comment for Carl. If you want to update your lab report, please do so.
Yes, doctor.
Yes, Carl.
In the lab report, question number 5.
Yeah, let me
lab 3.
Okay, I'm gonna open lab 3 so we can follow together. So
yes, I also got confused a little bit about this question.
Okay, lab 3, projectile motion, right? Okay.
Yes.
Just wait.
It's asked to.
Yeah.
I read the question.
Yeah, wait, can you see my screen? It's on my screen. Just give me a second. I decided to turn off my computer 1 week ago and I did not yet. This is so bad. I should turn it off at least once a week. All right, so question, yeah, because I'm not, it's like on since September. Yeah. So draw the 3 plots on the same graph. Okay, so basically when you do the graphs, I had many questions that the students asked. First of all, they needed to know what to plot.
It's number 5, not 3.
Number 5. Sketch a graph of your projectile showing the changes to the horizontal and vertical components of the launching velocity as it covers the full range. All right, so let me try to draw something. It's basically, although I don't have enough space, but I can still do something about it. So they want to see a graph of y versus x. Okay? Projectile, meaning by projectile, the actual projectile. They want you to show the changes of the horizontal and vertical components. Let me pick a certain color, maybe dark blue. For example, this is your velocity, right? And this is another velocity. Velocity is a vector that is tangent to my motion, tangent to my trajectory. Then they want you to show the horizontal component of the velocity and the vertical component of the velocity. The horizontal component of the velocity and the vertical component of the velocity. The horizontal component of the velocity, then the vertical component of the velocity. Hello, Joseph. So it's important to show that the horizontal component is constant all the time. And it's important to show that the vertical component of the velocity decreases as you go up and increases in the negative direction as you go down. And at the top of the motion, the vertical component does not exist.
I did it in a different way. Can I share my screen?
Yes, please share your screen and let's discuss it. It's a very interesting question. Go ahead. Joseph, you're good?
Is my screen visible?
Yes, it is visible.
I drew it like this.
So you did V versus Vx? No, you did V versus X and you showed on it Vx and Vy. How can I understand this? V versus X, how the velocity is changing with X. Okay, I like this. Your Vx is constant, it doesn't change. And your Vy decreases, then goes to 0. I love this, but this is very difficult for your friends to understand, but it's not wrong at all. You know, I like it. And I think you did the extra mile and you did even more than needed. So I wouldn't ask you to change it. I wouldn't ask you to change it. Half X final, I like this as well. Can I ask you something? Did you study this with somebody else? Because you are the first student to analyze projectile motion like that. Like I've never seen that in a book.
In baccalaureate class,
Yeah.
we had the projectile motion.
Yeah,
but I didn't have good grades.
Yeah, meaning grade 11?
Yes, I had a fight with the teacher and she kicked me out of the class.
Who's your
so
teacher?
I was obliged to pay.
Wait, who's your teacher?
Do you know her?
I don't know, maybe.
It's called Cathy.
Cathy, in which campus? On which school? Remind me.
Frère Mariste, Amshir.
Oh yeah, you told me you had a fight with your teacher.
Yes.
Why? Did you have any behavioral issues or you hated the teacher?
No, because I don't like French. That's what French, and I was copying all my exams in French classes, and she's the best friend of my French teacher.
Ah, she picked, yeah, all right.
Yes.
Okay, thank you so much. I'm gonna share my screen and maybe fetch a very, okay, let me find something that could be nice for you, although I don't want you to change your diagram, okay? I believe it's very nice to keep. Okay, maybe use this, move it a bit. I want to see if I can find the perfect diagram for the others to see us. Joseph, may I hear anything from you, please? So I'm gonna call it.
Of course.
Yeah, you're good, Joseph?
Thanks.
Okay, I'm gonna call it the velocity vector. I hope I can find a diagram to explain. Okay, what's wrong with Nazih? Okay, Nazih wants to know the link. Okay, wait a second. I need to send the link to Nazih. I need to send, okay, I'm gonna forward it. I have it ready. I'm sorry for the interruption, but apparently Nazih cannot make it. All right, this is what I was looking for. And I believe this is very beneficial. Let me show you this one. Let me find one that is easy. I want something with colors, maybe this one. So what they wanted you to do is the following, okay? They wanted you to show a regular projectile motion. They wanted you to show the velocity vector that is always tangent to the trajectory. And then you show the X and Y component, X and Y component. Here you have X, you don't have Y. X and Y, X and Y. It's important to notice that X is constant, the X component, you see? And it's important to show that the Y component is vertical up, getting smaller, then nothing, no Vy component. Then it gets negative and then increases in size. This is what they wanted you to show. Okay? All right, so now back to you. I suppose I did answer your question. Any other question related to lab 1 and 2 and 3?
I have, it's the same question, and for the graph of number 5,
Yeah.
but I did the graph, it was Y and X, but I did for the Vx, I did a straight line, and it's constant. And for Vy, I did it like a parabola. But not for each point, not like this.
Yeah.
I just did a straight line and PHY.
Maybe you did something very similar to what Carl did.
I don't know, but I did the Vx is constant. I can't share it now because I'm on my phone.
Share it. So you cannot share it. Okay, you cannot.
Yes, I cannot.
Okay, it's okay. I'm gonna look at it and I'm gonna write some comments for you. Like what Carl did, he did not answer the question, but everything that Carl did was not wrong. So I'm gonna keep it. I'm gonna look at yours. If there's nothing wrong with it, I'm gonna tell you it's all right. And if you have a mistake, I'm gonna show you where the mistake is. Okay? So I'm gonna be flexible with
Doctor,
it.
Okay, thank you.
Yeah.
If you can search on Google velocity versus time graph, you will see the same as Carl.
Yeah, but Carl did velocity versus position. And it could be versus time because time and position are proportional. Bravo, Joseph. I think you are totally right. Yes. Michelle, you're good? Hey, Michelle. All right. I'm happy that Michelle is with us. Any other questions related to lab 3? So again, I'm going to postpone the deadline until the evening. So if you want to do any modification, you can submit again. All right, waiting for Nazif to be with us. I think we're ready to start lab 4. Lab 4 is about motion on an incline. So, and you will be very happy because lab 4 is so much easier than lab 3 projectile motion. So motion on an incline. I'm gonna perform this theoretical part with your help. As you can see, I stopped doing PowerPoints because I believe it's very important for us to create the course together anyway. If you can help me, I will be very grateful. So I'm gonna start by drawing an inclined plane and ask you some questions. So this is my horizontal plane and this is a certain inclined plane. I'm gonna simply call the angle alpha or anything you want me to. In the lab, I'm gonna use a cart. All right. So now my question for Joseph is the following. Joseph, if you have a cart just rolling down the incline, can you help me out? List the forces on the cart.
Weight.
The weight, all right. So I'm gonna call it the weight mg. So it's m times g.
And the reaction of the floor, it's perpendicular to the incline.
Okay, reaction of the support or of the floor, it's always perpendicular to the incline. Any other force?
Is friction or something or not?
All right, I'm gonna draw friction very thin because I'm gonna ignore it throughout the experiment. If you ever ignore friction, I'm gonna say that this is a source of error. You're gonna see on the video that the track is very smooth and the cart has wheels that are super fast, which means that friction is really reduced to a very, very small value. I'm gonna ignore it and this is a source of error. Without friction, my system is gonna be ideal. With friction, my system is gonna be real. And real systems are what we can see in the experiment, right? Okay, so now I need somebody to remind me about the acceleration in free fall. Okay, and this somebody is Michelle. Michelle, when you do free fall, what is the acceleration equal to? Michelle, not with us, Dana. All right, 9.8.
Yes, miss.
Yeah, so I was actually asking Michelle something and he answered. I can ask you the same question for you, Dana. Free fall, what's the acceleration in free fall?
It's 9.8, miss.
Yeah, it's 9.8 and I'm gonna say meter per second squared. It's basically equal to g. Do you know the reason why? Can you prove, anybody can prove why acceleration is equal to g? So Joseph is saying negative g. In other words, he's saying it's downward. So the negative is simply to say it's downward. By the way, in physics, we don't have negative values. It's basically magnitude and direction. So the magnitude is g and the direction is downward. To make our life easy, we use minus for direction. Now back to free fall. Anybody can tell me exactly how to prove that A is equal to G?
Yes, I can.
Yes, can you try?
We have the sum of the forces are equal to MA.
Okay, so you're using the fact, the Newton's second law, although we did not do Newton's second law yet in the lab. So sigma F is equal to MA, and this is a vector equation. How do you proceed?
In the free fall, we don't have any force other than the weight.
Okay, so I'm gonna write only weight to be equal to MA.
Equals mg.
Yes, and the weight is equal to mg. Yeah.
So g equals a.
All right, so you cancel out the m's and you can see that the acceleration is equal to g in magnitude and in direction. Can we try to do the same thing for the incline? So this is basically for free fall, right? Now we're gonna try it for the incline, and it will be a little bit difficult. How about I remove the friction to make your life easy? Remove friction and use a very light color to draw the x-axis. I'm gonna take the x-axis along the motion. I'm sorry because I have to do that. You would hate it because usually you like your x to be horizontal. Okay? All right, now I'm gonna write the x and y component for each, or how about you help me, Carl, write sigma F equals MA for the incline.
The angle or not?
Yeah, so the angle is here. Let's call it theta. All right. So what are the forces in my case? There are two.
Projection of R is 0.
All right. So let's project the whole thing on X. This is what you want, Joseph. All right. So I'm gonna say there's no R. And what is the projection of the mg on X?
Cosine 1. Cosine.
So mg cosine theta. All right. So, but which theta are you taking into account? Maybe this theta.
Yes, not in the triangle.
Okay, I'm gonna call it alpha because this angle is different than this. So Joseph is saying if I do
we need sine. It's sine.
All right. So what Joseph is saying, and Joseph is not saying anything wrong, he's saying that mg cosine alpha is equal to ma. All right. So let me explain again. Joseph, and I have to agree with Joseph, can see that this is the x component of mg, and it's adjacent to this angle that I'm gonna call alpha, and it's mg cosine alpha. Okay. Now, maybe you can agree that alpha and theta are actually complementary. So cosine of alpha will be equal to sine of theta. So I'm gonna change that to mg sine theta to be equal to ma. Now for the students who hate all this, I'm gonna tell you a secret that usually my other students actually follow. For the inclined plane, if you find geometry difficult for you to grasp, simply you should know the final answer. Like my other students will never go through the derivations. They know that for the weight along the x-axis is mg sine theta. They don't think about it. And theta is the angle of the incline. Okay, so in other words, just know it by heart. You don't need to derive it every time. Like everybody on planet Earth knows that the mg of the incline is mg sine theta. Okay, and now let's cancel out the m's. What do you end up having? Yeah, anyone? I need the acceleration.
It's mg sine theta.
It's gonna be g sine theta because the m will cancel out. Okay, so it's gonna be g dot sine theta. Now I want to show you something that is very interesting. For free fall, acceleration is g. For the inclined plane, acceleration is g sine theta. And let me tell you, all physics students know this. Even if they don't know how to derive it, they know free fall, A is equal to G, incline A is G sine theta, all right? And this is key, it's like very important. Now let me go to the lab report, and I'm gonna keep this file, share it with the other students. I'm gonna fetch lab 4, motion on a frictionless incline, and eventually show you the video. All right, so they show you the incline, they show you mg, they don't show you the reaction, but they actually explain that the net force is one component of the weight, and the component is mg sine theta. So maybe this is not enough. Maybe you need our whiteboard in here to be able to explain it well. They explain that if you don't know theta, you can easily find the height and the length and find theta. But don't worry, for the experiment, we have a protractor and you will be given theta directly. They explain the procedure. I'm gonna do that in a video. And eventually you have the lab report. So what you need to do, you have to create different angles of the incline. Throw or just release your cart. It's gonna accelerate down the incline. You're gonna do it 5 different trials, okay? So you're gonna do trial 1, 2, 3, 4, and 5. Find the acceleration. I'm gonna show you how later. And then find the average. I need someone, and this someone is Michelle, to remind me how to find the average of 5 different values. Michelle, can you speak up? Michelle is not here. Dana, can you remind me how to find the average for 5 different trials? Hello, Dana? Maybe,
okay.
Yeah. How do you find the average?
So for the 5 different trials, or each different trial, or?
Yeah, so basically you are given acceleration 1, 2, 3, 4, and 5. You need to find the average. How do you do it?
Right, so you add all of the values that you get and then divide that by the number of values. So that's all the values divided by 5.
All right. And how do you find the error on the average?
You find the error by, okay, I'm going to try to play this by memory. It would be the average 1 minus the actual value plus average 2 minus the actual value plus average 3 minus the actual value, all to the square root and over and minus 1.
All right. Let me show the other students how to do it. Maybe they need help with this one. And let me fetch any lab report who has it. I have it here in Physics 306, just the first chapter, because it's good to have a picture. Maybe I can take a screenshot of it so we can keep it on our whiteboard, whatever. So what Dana is trying to explain is how to find, this is it, it's in red, how to find the RMS. RMS means the root mean square error. It's the uncertainty for any average. So we actually do this only for averages, all right? She was explaining what DI is, she was explaining what N and N minus 1 is, and yes, Carl, we can simply do it on the calculator. Maybe I can throw this YouTube link that you guys already have in the chat, in case you lost it. Where do you find this link or anything related to the RMS? If you go to Lab 0, on Blackboard, you already have the link. It helps you find the RMS error, which is the uncertainty on an average. Okay, so watch the video. It's me explaining how to do it on a calculator and how to do it with a simple calculation. What Dana was trying to explain. Okay, so N is the number of measurements, and DI is the deviation of each and every measurement from the average. Now back to our lab report. You were supposed to, I'm gonna give you all the accelerations. You find the average and the error on it. They want you to know the acceleration experimental. You say it's the average value and the error. You write exactly the same thing. Now, how do you find the theoretical answer? How do you find a theoretical?
Miss, did you ask me?
I'm asking anyone. Maybe Nazir, because Nazir just joined us. I hope Nazir, his microphone is functioning. So, again.
Professor, hello, Professor.
Hello, Nazir. It's great to catch you.
Okay, to find the theoretical, you have to measure it.
All right, so basically, didn't we just say that the acceleration is g sine theta? This is the theoretical equation, all right? So I'm gonna use this equation. So how about I type that this is the theoretical acceleration. So I'm gonna go back to my lab report and say, I'm gonna do G sine alpha, or sine theta. I know theta, it should be given to me, and G will be 9.8. I can easily find the theoretical value. Now I'm expecting the experimental to be similar to the theoretical. When they say compare, so every time they ask you to compare, you do the percentage difference. And I need someone to remind me what is a percentage difference. How do we do percentage difference?
Theoretical minus experimental over experimental.
Or over theoretical. In biology lab, maybe you divide by experimental. In physics lab, I'm gonna take the theoretical to be our reference, and eventually take the absolute value. So if it's negative, it's okay, just take the absolute value and multiply by 100 to make it a percentage. Okay, we want to make it a percentage, we multiply by 100. So compare your experimental acceleration to the expected value. Comment on the possible sources of errors. Here you have to list at least 3 sources of errors. All right, think about it. Can you give me some sources of errors? Why do you think my experimental acceleration would be a bit different than the experimental acceleration, the theoretical one?
Because of air resistance.
Air resistance, why not?
Correct.
Yeah, why not? Because air resistance would affect my motion. What else?
Also the material of the projectile?
No, not projectile, you mean the cart on the incline.
Oh, sorry, yeah, the cart.
Yeah, so it may create some friction probably.
Yes.
Yeah, so friction and air resistance. Do you remember? I don't know.
But
did you receive my email? 1 second. This email was very interesting. Let me check it out. It's your class. Where's your class? Where's your class? Magnetism, tips, mechanics. I sent you this. Did you read it? These are tips about what could be the sources of errors. Read them out and try to pick at least 3. Okay? So what does it say? It says friction and air resistance. You can reduce it, but you can never get rid of it. Horizontal bench. I'm assuming my bench is horizontal, my desk. Maybe it's not. Gravity 9.8. Who told you gravity is 9.8 on campus? Maybe it's an assumption. Any other given that I'm not trusting? Measuring tools. All measuring tools have limited precisions. Like here, I found the acceleration using the motion sensor. I'm going to show you how on the video. I don't trust the motion sensor. It has a limited precision. I'm using my protractor to measure the angle. I don't trust it. It has a limited precision. Do I have any human error? Am I measuring time, or am I using my slow reaction time? I don't think so. So try to have a list in front of you and pick some sources of errors. 3 sources are enough, okay? All right, now back to our lab reports. Deduce the effect of increasing the angle. So you will check theta 1, theta 2, theta 3. Maybe the angle is increasing. You're gonna discuss the effect. What happens to the acceleration? Now you're gonna add a mass. Maybe add more mass to your cart and see if anything would change. Deduce the effect of the mass, but I'm gonna give you the answers, so probably it will be easy for you to discuss. Here they want you to devise a procedure. By what do I mean by devise a procedure? You need to come up with a thought experiment. All right? So it's a thought experiment. Just describe how the experiment is. Like, what material would you need? Maybe you can draw a picture of the setup and tell me, what do you actually measure? What do you actually measure? Okay? And they want you to find a way to prove that the acceleration is inversely proportional to the mass, and so on and so forth. So think about it, because maybe this experiment would not be enough to show you how acceleration is related to the mass. So for free fall and for incline, the acceleration is not related to the mass, and you can see it in our equation. Acceleration is g sine theta, so it's not mass dependent. You have to think of some other experiment where acceleration will be affected by the mass, okay? So what else do they ask you? And that's it. You see, the lab report is super easy. All you have to do, you don't need to plot, you just need to do average and RMS. Now let me go and find the experiment itself. I'm not gonna watch it with you because I know you can watch it later. I just want to show you a few things. Maybe go on fast forward. Do you see the track? Yes. This is the protractor. This is the cart. And you have here a black obstacle attached to the track just to make sure for the cart not to go down the floor. And I have a motion sensor in here, and you will see, you will end up with a VT graph, an XT graph, and an acceleration T graph. I'm gonna go fast forward because you can watch the video later. I'm explaining how friction is reduced. I'm explaining how the protractor functions. I'm showing you the mass of the cart and how fast the wheels are. I'm showing you how I change the height and therefore the angle. I'm gonna show you a trial. I'm explaining how the motion sensor is connected and how it measures. By the way, the motion sensor, what does it give me? Maybe ask Leia about it. Leia. So we're discussing, Leia, the...
Yes.
Yeah, so the motion sensor, do you remember which graphs does it give you? What does it measure, the motion sensor? It's okay if you don't know, and you can try.
The velocity?
Yeah, it gives me velocity and position and acceleration. So every time I have motion sensor, it gives me the VT graph, the AT graph, and the XT graph, okay? I'm gonna fast forward to show you the graph, closed lookup. So here I'm trying to explain the procedure and not the graphs yet. So you're gonna see how I release the card, how I press record, and how collision happens. So basically, yeah, so the collision doesn't show. And I can, okay, maybe the track to be sliding on the table and therefore my angle to vary. So I will click record and the release holding the cards a bit. All right, in this case, I showed all the collisions, although all you need is maybe the first motion. But usually the first motion is full with errors. Maybe the third or the fourth one is gonna be easier to see. Now a closer look up to the screen, you see the XT graph, and it's very well explained in the figure, in the movie. It shows why the motion is not linear in time. So the motion is like this, then you have collision, then again closer to the motion sensor, then away, collision, closer, then away. And you can see that you have some energy lost after each and every collision. The acceleration, I would zoom in to show you that the acceleration is supposed to be constant. Constant acceleration is G sine alpha, collision, G sine alpha, collision, G sine alpha. And you see G sine alpha is constant. It doesn't change. It's only that it's becoming shorter and shorter because you're losing energy after every collision. This is very important to see. This is the VT graph. And you will be given 2 points. You find the slope. So the acceleration that I'm gonna give you here is the slope and the VT graph. So I'm gonna use the VT graph on this video to find the slope. And you can see that here it's moving down the incline, no, up the incline, then down the incline, collision, up, down, collision. Up the incline is negative velocity, down the incline is positive velocity. And this tiny dot where it hits the x-axis is where it stops for a second at the top of the motion. All right, so these are very important to understand. Let's continue. So it's explaining how the thing is going, and I'm explaining here how you take 2 points to find the slope. And eventually, I'm gonna show you how I add some masses to my system. I tried with 2 masses, it was too heavy, and it went out of the track. Same motion while recording your values. You click on record, you release the card, it will bump into the obstacle. Be careful, it's gonna be very heavy. Maybe. Okay, I repeated the experiment with less mass to see what will happen. And eventually I'm gonna record and send you the answers, okay? So that's it. Now with less mass, it did not go out of the track. Okay, and that's it for the experiment. So the experiment is very easy. I'm gonna give you feedback about lab 2 because I did not correct lab 2 yet. You're still submitting lab 3. I'm gonna change the deadline until the evening, so you can have some time during the evening to update or change your work if needed. And that's it. Anybody has any question?
We are not going to have classes on campus.
Actually, I already sent a survey, a question for all the class, and maybe you read the question. And the question was, who would like to go on campus? 2 students answered by yes, and 3 students answered by not possible, and the remaining student did not even answer my question. And then we decided 2 out of 8 students, maybe we should not do it. But if you insist, who was talking? Was it you, Carl?
Yes.
So do you insist to go on campus?
No, I don't insist. If all the class cannot go, of course we will not go.
Actually, I'm gonna try with my other sections, not other sections, other classes, physics lab, to go on campus, because I have another class, they are 20 students, and I think maybe half of them would like to try. So if you feel, Carl, that you want to come, probably I can open something for you, although I need to go back to the admin. You can create your own results, and you will have the bench for you alone, and the lab is gonna be clean before you come and clean after you leave, and you're gonna be away from any human being, away 2 meters away with your mask on. I don't see why not you coming to the lab. All right, but I need to give you feedback, and you need like to know if we're going, or so far we're not going to the lab. All right, because that was the answer of everyone else. Okay, anyone other than Carl would really like to go on campus? And for the midterm and final exam, I don't know yet. We have a midterm sometime soon, maybe in 2 weeks or 3 weeks. I'm gonna tell you more about it next time we meet, okay? Any comments?
Okay.
Professor,
Yes,
I have a question.
Yeah.
About the graph. I sent it to you.
Yes,
The graph, the
yes.
corrected one.
Yes,
The corrected graph.
so basically Nazir sent me a question. Let me go to my email again. So Nazir wanted me to discuss the following, and I asked Nazir to ask me this question during class. So Nazir, this, you would like to upload this on your lab report, right?
Correct, yeah.
Okay, so
it's a correct one.
okay,
Yeah.
so how about you fix your lab report and submit again, because you can do that. Like you can submit as many lab reports as you can, and I will correct the last one you submit. And I'm gonna change the deadline until 11:30 p.m. Do you think you can do that? Do you know how to insert this in your document? I think you know how.
Yeah. I already do it. I already did it. It's on the document.
Okay,
Yeah.
but then I see that you have some questions. Do we have to mention the source of error? If they ever tell you what are the sources of errors or comment on the sources of errors, yes, do mention them. If they don't, you don't need to mention them. Okay? Do you want me to check on the lab report if the question is there?
All right.
You're fine, Nazir? Do you want me to open lab 3 to see
It's good, yeah.
Yeah. So let me...
It's good, actually.
It's what? Okay, so let me see where... All right, so they say draw the 3 plots, deduce the angle, compare it to your expected value, sketch a graph. I don't see any question that says list the sources of errors. List the sources of errors. So you don't need to list the sources of errors. in all lab number 3. Okay, did I answer your question?
Yes, no. Professor, thank you.
All right, so may I ask you who is Sarkis? He helped you do the graph? Which is okay.
No, it's me, but I did it in this computer.
Okay, all right.
In this computer.
If you need help on how to use Excel or how to do any plot, please let me know. I can send you a very quick video explaining how to do it, okay? I was expecting at least one student to ask me how to plot 3 graphs on the same Excel sheet. So if you need any help, let me know, all right? Remember, those lab reports are not exams, neither assignments that are rigidly graded. These are labs where I have the chance to help you out, to be your advisor, and to push you in a certain direction before our final exam or midterm. All right, so the purpose is to learn some skills. That's why I'm modifying the deadline a bit, so I can have some time to answer your questions before you submit. Any other question? I know Joseph had a question, right? Or did I answer it already?
Good, doctor.
You're fine, Joseph?
I am.
Okay.
Thank you.
All right, you guys, you are dismissed. So...
Thank you.
Have a good day. Have a good day, Professor.
Listen, I'm noticing that
Thank
you're
you.
losing the link to the class. By the way, the link is always in our Blackboard. If you go to the announcements, go to the first announcement and the link is there. Like if you ever lose it in the future, or please write it as a note somewhere. It shouldn't be difficult. It's Jessie.Haddad. So check the announcements. It's there. Maybe I can show you if you would like to stay, because I know that probably you don't want to stay. Did I close my Blackboard? No, it's here. So this is my Blackboard. You go to your class. This is where your class is. Let me move a bit, my dashboard. Yeah. So this is your class, mechanics lab. If we go to the announcement, by the way, they're never hidden. Like you can go back to the old announcements we have. If you go back, it says that this is the WebEx. So Dana and Nazih, if you ever lose the WebEx, just take it from here. Okay?
All right.
All right, so you will
Okay,
never
thank
ever
you.
lose it. Okay. Thank you so much for today. I'm gonna update now the deadline for lab number 3, so you can have more time to visit and revisit. And yes, you can submit again as many times as you want. Thank you so much. Enjoy your evening.
Thank you, Miss. Have a good week.
You too.
Thank
Bye.
Thank you, doctor.
Bye.